Hello everyone. The imbalance between matter and antimatter is a profound mystery in cosmology. According to the Big Bang theory, matter and antimatter should have formed in equal amount, but it is not so. CP violation plays an important role in understanding this imbalance. So let's see in this video. What is the relationship between CP violation and matter-antimatter disequilibrium? But before that, it is very important to understand CP violation. CP violation was first observed in 1964 by James Cronin and Paul Fitch in the decay of neutral cones. A CP violation refers to the combined symmetry of charge conjugation and parity. Charge conjugation means a transformation that converts particles into their antiparticles. For example, an electron becomes a positron, and a transformation that reverses the spatial coordinates of the particles is called parity. We can also say that if the particle is moving left, then it will move right in this transformation. CP symmetry means that the laws of physics must be symmetrical if particles transform into their antiparticles and the coordinates are inverted. But CP violation refers to its inversion. That is when the particle is replaced by its antiparticles and their spatial coordinates or directions are reversed, so the laws of physics behave differently for particles and antiparticles, which shows that CP symmetry is not conserved. For example, when CP symmetry is conserved, so the rate of decay of the neutral cones and their antiparticles is found to be same when observed in a mirror image. And when CP symmetry is not conserved, so decay rates were found to be different. That is, the CP symmetry is violated and the laws of physics are not same for particles and antiparticles. This is called a CP violation. In any decay or reaction, if CP symmetry is violated or if a CP violation is involved, the decay rate of matter and antimatter is different. Therefore, CP violation plays an important role in matter-antimatter asymmetry by helping with some processes and experiments. We now understand why matter dominates the universe and how it relates to CP violation. CP violation plays an important role in this disequilibrium through a process called baryogenesis, the process or theory that explains the predominance of matter over antimatter in the universe. Here we know in detail how CP violation interacts with this phenomenon. Number 1. Sakharov conditions. In 1967, Russian physicist Andrei Sakharov proposed 3 conditions that must be satisfied for baryogenesis to occur. It helps explain the dominance of matter over antimatter. Number 1. Baryon number violation. For baryogenesis to occur, there must be interactions that do not conserve baryon numbers. Interactions mean processes that change the states of particles. These interactions trigger the creation or annihilation of baryons without an equal number of antibaryons, which is necessary for an asymmetric creation. And there are some reactions that do not conserve the baryon number. According to the grand unified theories, decays of heavy particles lead to an excess of baryons. Number 2. CP violation. Any process without a CP violation can produce a number of baryons and antibaryons, but CP violation forces these processes to produce more baryons compared to the antibaryons, which contributes to the dominance of matter over antimatter, and CP violating interactions play an important role in baryogenesis. Number 3. Out of equilibrium conditions. As the universe expanded and cooled, it went through phases where it was not in a thermal equilibrium. The asymmetric production of baryons on antibaryons during these phases was not immediately eliminated by the annihilation process, allowing additional baryons to survive. Number 2. CP violation in early universe. During the early moments of the universe, conditions were so extreme, which allows high energy particle interactions. A CP violation in these interactions may lead to a slight preference for creating a matter over antimatter. For example, electroweak baryogenesis. This theory suggests that the CP violation occurred during the weak phase transitions, when the universe was about a picoseconds old. During this phase transition, interactions involving the weak nuclear force and the Higgs field can favor the production of baryons rather than antibaryons. Number 3. CP violation in quark interactions. In the standard model of particle physics, that is the 3 fundamental forces that drive the universe, proposes many mechanisms for CP violation through the CKM matrix. CKM matrix means the unitary matrix containing the information on the strength of the flavor-changing weak interactions, which describes the mixing between different types of quarks. This matrix allows the CP violating process in weak interactions, the first of which is Coulomb decays. CP CP violation was first observed in the decay of neutral cones. Cones are also called K-meson. These decays showed that the rate at which cone particles decayed was slightly different from their antiparticles, which provides direct evidence of CP violation. Number 2. B-meson decay. More recently, experiments on B-meson, i.e. bottom quark containing particles, have shown CP violation. This observation shows that particles and antiparticles have different decay rates or different pathways beyond the standard model. Although the amount of CP violation observed in the standard model is significant, however, it is not significant for the matter-antimatter imbalance in the observed universe. So physicists are looking for theories outside the standard model, one of which is supersymmetry. This theory predicts new particles like superpartners, a group of hypothetical elementary particles and interactions that can enhance CP violation. Number 2. Leptogenesis. This hypothesis describes CP violation in particles such as lepton sectors like electrons and positrons. Leptogenesis suggests that the CP violating decays of heavy neutrinos in the early universe may have created an imbalance in the number of leptons and antileptons. Then through the Sphaleron process, the lepton asymmetry is converted into a baryon asymmetry. It plays a role in matter-antimatter asymmetry. So this was the CP violation and standard model experiments, where we observed matter-antimatter asymmetry under these conditions. In the CKM matrix, we observed that B-meson and their antiparticles show different decay rates and different pathways, and demonstrating CP violation as well. This behavior contributes to the dominance of matter over antimatter. Similarly, in the early universe, CP violation processes that involve heavy particles led to an excess of baryons over antibaryons. During thermal non-equilibrium, these processes prevented the annihilation or elimination of baryons and antibaryons. This established an asymmetry, due to which additional baryons and antibaryons survived, but the decay rate of both is different, so matter dominated over antimatter in the universe. Despite all this, we said at the beginning of the video that the matter-antimatter disequilibrium in cosmology is a profound mystery, because the amount of CP violation in the standard model is insufficient to explain the observed matter-antimatter imbalance, because the prediction for particles like B-meson was for a small amount of particles. This prediction is not strong for such a large universe. So physics predicts some new theories outside the standard model, like supersymmetry and leptogenesis. Supersymmetry predicts new particles and interactions that can enhance CP violations, while leptogenesis involves a CP violation in the decay of heavy right-handed neutrinos, which creates a lepton asymmetry that can be converted into a baryon asymmetry by the Sphaleron process. These predictions are believed to be stronger because they deal with heavy particles. So CP violation is an important factor in this process that lead to the matter-antimatter imbalance in the universe. Evidence for this comes from B-meson decay and theories outside the standard model. Researchers are trying to solve this puzzle by doing various experiments. So far, this is an unsolved puzzle of matter-antimatter imbalance. So this was today's video. How did you like this video? And if you like this video, so please subscribe to us.